Okay, now that the cheering has subsided because of what you just saw with respect to problem number 4 and how the test software is able to handle multi-fluids and perform the energy balances and the entropy balances associated with the system. I'm now going to take a look at the final problem. And the final problem that you had was a ideal Rankine cycle. Okay, water is the working fluid. Saturated vapor of a given mass flow rate enters the turbine. And so that's, if we look at the various state points here, entering the turbine, it's state 1. We know something about the water. It's saturated vapor, which corresponds to a quality equal to 1 at a given pressure, and that pressure is 6 megapascals. And so we know the conditions here at state 1. It goes through the turbine, and since the turbine exhausts to the condenser, and the condenser has a pressure of 80 kPa, we know that at state 2, the pressure is 80 kPa. Because this is an ideal Rankine cycle, we're making the assumption that it stays in the condenser until it is fully saturated liquid, quality 0. We also, because the ideal nature of this cycle, we make the assumption that through the turbine, entropy does not change. It's an isentropic turbine. So that gives us the entropy at state 2 as well as the pressure. So it specifies everything we know through the turbine. The difference in work, the difference in heat transfer, or the enthalpy is just going to be equal to the work because, again, for the ideal Rankine cycle, we assume no heat transfer. What happens in the condenser also does have heat transfer, but no work, and enough heat transfer comes out such that the enthalpy change is related to the heat transfer pulled out. Again, state 1 and state 2 and state 3 as well as 4 have flow rates of 100 kilograms per second. What happens in the pump? We know the conditions coming out of the condenser, and the pump, we are going to assume that the pump is also ideal isentropic, and so we know the entropy at state 4, and we know that the pump raises the pressure back up to the highest pressure in the system, which is the turbine entrance. So the pump goes from the 80 kPa to the 6 megapascals without any heat transfer, and all the work goes into the raising of the enthalpy. Between state 4 and state 1 is where heat transfer comes in order to bring the fluid up to the elevated temperature associated with state 1. And that elevated temperature is the saturation temperature associated with a saturation pressure of 6 megapascals. So we have all the information that we need with respect to the various state points. And so now we get to go into the test software. And now when we ask ourselves system, substance, process, our system is an open system. And that open system basically is going to follow the blue lines down. Now, this is a specific type of open steady system, and it is a vapor power type of system. So we're going to be picking this one here. We also know what the fluid is, the substance, and the processes that are occurring in the 4 devices we will then also specify. And so we have a vapor steam power cycle. We're not a gas cycle, and we're not any combination. And so we pick a phase change model because it is liquid water going through phase changes. And again, we have a number of different examples, but we go directly to the assigning of the states. And so state 1, we know, is the fluid. In megapascals, we know that it's 6 megapascal pressure. And as given in the problem, it is the saturated state with a quality equal to 1. We also know in this problem that the m dot is 100. And so we have everything that we need to know about state 1, entrance to the turbine. And most importantly, we know what its enthalpy is. We now go through the turbine, and what we know about the exit of the turbine, or the entrance to the exit of the turbine, is that it is expanding to the pressure of the condenser, which is 80 kPa. And as it goes through the turbine, we know that its entropy doesn't change because it's an isentropic turbine. And so the mass flow rate, nothing leaks out, and so the mass flow rate is m dot, as it will be for all 4 states. And so now we know the exit of the turbine. We see the enthalpy is dropped to this level here from the original enthalpy. And now we're ready for state 3. State 3 is the entrance to the pump. And we know that the pressure is the same as what we assigned at the exit of the turbine. We also know that coming out of the condenser, it's all liquid. It's just reached the saturation point, saturated liquid point. The m dot is equal to m dot 1 all the way around the horn. And we now know the enthalpy associated with what happened in the condenser. It went from an enthalpy of H2 to an enthalpy of H3. So now we're at the entrance to the pump. One of the things we know about the pump is isentropic. And so S4 is going to be equal to this value here. So when we go to what we know about state 4 is it brings the pressure up to the highest pressure in the system, which is the incoming turbine pressure of P1, which is 6 megapascals. And again, the entropy is equal to the entropy coming into the pump. And as before, the mass flow rate is the same mass flow rate around the horn. And so now we have the outgoing condition from the pump. Okay, we see that the temperature is 93. What's going to happen in the boiler is it's going to bring up the temperature to this value here. And so now we have all 4 states assigned. Now what you'll notice is there is a cycle panel as well as device panel. And so in this particular case, well, if we wanted to see the state points, we can go to the graphics panel, and there is the TS diagram. And so in this particular problem, you were asked to sketch the TS diagram. And if I were to put a constant pressure line through state 1, that would be the 6 megapascal line. If I were to put a constant pressure line through state 2, which is the exit of the turbine, which is at the 80 kPa, you then see that there is the 80 kPa line. Okay, obviously, this ideal turbine is one in which the expansion through the turbine is under the dome, which isn't usually what happens. But again, it's an ideal scenario. This is the isentropic expansion through the turbine. We then have the condensation occurring to this point, and state 4 is just a little bit higher than that because all those pressure lines are right on top of each other in reality due to the incompressible nature of liquid water. Okay, so we have our TS diagram, And now we can go through and we can assign our 4 devices. The first device is going to be the turbine. The turbine goes from state 1 to state 2, and what we know about turbines, the ideal turbines, is there's no heat transfer. And so this immediately tells us that the work, if I put it into megawatts, because we know the flow rate, it's a 68 megawatt turbine work output. Again, no entropy generation because it's an ideal. We go to state 2, which is the condenser. At state 2, we go from state 2 to state 3. And we know that there's no work in that device. It's just a heat transfer. And we look and we see in megawatts, 170 megawatts are rejected as it condenses. So we had some work. We have now this heat transfer out of the system. In addition, some entropy generation in that particular process. Okay, so now we go to our our next device, which is now the pump. And the pump goes from 3 to 4. And the pump is adiabatic also. And as we can see here, the pump is a very small amount corresponding to the work of the turbine. So the back work ratio that you might have heard Professor Tran talking about is very, very small for this particular case. A very small percentage required to do the pumping. And again, because a pump is pumping compressible liquid. And so no entropy generation because it is an isentropic process, adiabatic isentropic process. And then finally, we then have the final process, which is coming out of the pump to the turbine, is now the boiler. And we know that the boiler, no work occurs in the boiler, but what does occur in the boiler is a whole bunch of heat transfer is transferred to the fluid to bring it up to that elevated temperature at that high pressure, with again some entropy then being being generated at that particular case. Okay, so now that we have defined all of the 4 processes, these 4 processes are typically either a heat transfer or a work process. And so the cycle panel is going to look at the entire process from 1 all the way around through 4 back to 1. And when you go to cycle, the cycle as a power cycle, it keeps track of everything for you. And so as you can see, it looks at the heat transfers, and if I put those into megawatts, we see that this is the heat transfer going in the boiler. This is what's rejected by the condenser. And so the net heat transfer is this, the difference between those two. The work, if I go into megawatts, this is the work going in to the pump. Now, these works and heat transfers they always show them as positive, even though we know that this is negative, this is positive, this right here is a negative work, and then this is the work coming out of the turbine, which is the 68. Okay, and so the net work becomes 67. Now, this is the statement of the cycle, first law for a cycle. The net work and the net heat transfer are equal to each other, as you can see there. This back work ratio that I mentioned, that back work ratio is equal to this value divided by the work, the work that's actually generated, 68. So some of that work, this very small amount, it's less than 1%, has to go back into the pump. So you don't get all of that out. You get this out. The thermal efficiency then is calculated, and it also determines some of your maximum temperatures, your minimum temperatures, as well as the maximum pressures and associated with, and minimum pressures associated with the system, along with the total generated entropy value. Okay. This eta Carnot is related to these two temperatures. And so you might have remembered back when talking about the first law in chapter 6, there was an expression for the Carnot efficiency for a cycle operated between two temperatures. And so if you put in the minimum temperature here and the maximum temperature here, you get the Carnot efficiency of 33%. But what we're really interested in is the thermal efficiency of this ideal Rankine cycle, which is the actual work, which is this value here, divided by the heat transfer in. And so those two, that ratio is 28.4%. And so back to the problem, we've sketched the TS diagram. The rate of heat transfer to the boiler was shown, it was calculated. The net power generated, again, the net power is the difference between the output power minus the pump input power. And then finally, the thermal efficiency of the cycle was calculated in the cycle panel. Now, in a problem like this, if you knew the flow rate of the water, you could figure out, you could determine the flow rate of the water if you knew the incoming and outgoing temperatures, because you know how much heat transfer occurs. And then again, in the boiler, this would be a combustion problem that we would handle in one of the later chapters, how much heat transfer had to occur, how much fuel and air had to burn in order to generate or release that amount of energy. So that then finishes up that particular problem.